I'm going to describe some work we did the last few years at Harvard. We've been looking at neural networks for a while now at Harvard, and we've actually got some really nice collaborations with machine learning faculty in the department, which is really nice. Slides. So I think we're probably already into the third or fourth machine learning intro slide, so I go quite quick. Here's mine. So speaking sort of about deep learning specifically, I think it's this virtuous cycle that probably led us to deep learning. So we have sort of access to more compute and bigger data, and this has allowed us basically to train sort of ever deeper neural networks, which are sort of capable of solving increasingly sophisticated problems. And, I think actually neural network inference has sort of rapidly become such an important workload that we've already seen hardware specialization. So we've seen GPUs that are optimized for 8-bit integer performance. And we've even seen dedicated ASICs as well, which is really interesting. So this is the Google TPU here. And I think, deep learning's been a really huge success. It's all about supervised learning. It's mainly about inference as well. So training, we train these networks once, and then they're used many times on our devices. And generally, deep learning's been quite synonymous with, very big iron CPUs and GPUs in the data center, and very, very large neural networks. So what about embedded devices? Well, mobile and IoT devices, probably the fastest growing, biggest compute platforms on the planet. And neural networks are really important to a lot of the use cases for these devices. They basically allow these devices to understand the real world around them. And this is really important to these use cases. So most of these devices currently, neural network inference, we usually actually perform in the cloud, as others have already mentioned today. So we take some sensor data and we send that up to the cloud where we do the classification, and then we send the result back again. So this kind of works okay, but it has a few drawbacks because it incurs sort of some latency to do that, and it actually takes more power because we have to communicate the data. And there's also sort of security issues with sending photographs of cats into the cloud. So we really want to try and bring inference part right now back onto the device. And in particular, I think, as another presenter mentioned this morning, always-on sensing is quite a big driver for this. But it's really not easy to do this because neural networks tend to be very large, and they require a lot of compute, a lot of multiplications. So for lower-end neural network applications, we actually quite different to a lot of deep learning. So deep learning is usually about end-to-end networks that take in very raw data and they try and learn everything directly. For a lot of low-end applications, we still often use feature extraction. So these are handcrafted features, and they often lead to less good results in terms of accuracy, but they're much more compute efficient. And so a typical sort of always-on inference application at the edge might look something like this. We acquire some sensor data, we perform some pre-processing, some kind of feature extraction, and then we run some classifier. And really, it's this classifier at the end of this pipeline that really consumes all the compute. So the neural networks themselves, as I mentioned earlier, they're usually trained offline ahead of time, and that's done once or twice. And then they're deployed, and inference is performed many times. So the training of the network I won't really go into, but the training itself sort of does impact the hardware in as much as there are some trade-offs that the application designer has to make between the accuracy and basically the size of the workload. And I think one of the key points here is that accuracy is often critically important. So it's really important we push towards high 90% accuracies, or else people get frustrated with the user experience. So for the remainder of this talk, I'm going to describe a piece of work we published recently. So this is an example. It's kind of a deep dive on a dedicated hardware accelerator. So if you really want to hit power budgets that you can do these things on mobile devices, then this is one way you can go. So from an architecture perspective, deep neural networks are quite interesting workload. So they have some features that architects really like, so they have lots of parallelism, and there's lots of opportunities for data reuse, specifically in CNN graphs, but also a little in fully connected. And they operate on sparse data, and they can use small data types. And they also, interestingly, they're designed to be tolerant to noise. They have certain inherent algorithmic resilience. So I think quite a few presenters have already touched on these topics. I think this is more evidence that adds weight behind this. Okay, so here's the outline for the remainder of the talk. I'm going to describe our hardware accelerator in more detail, focus on those areas of parallelism, sparsity of small data types, and algorithmic resilience. I'll show some measurement results from a recent test chip, and I'll conclude. Okay, so here's a sort of a toy example of a fully connected neural network graph. So we have sort of input data comes in on the left-hand side with the green nodes. And we have these layers of what are called hidden neurons in the middle. And then we have the output classes on the right-hand side. And basically, the network is giving us probabilities that the input data falls into one of multiple classes. And each edge in this graph represents a multiplication with a unique weight, and each node is a neuron. And clearly, there's a huge amount of parallelism in this graph. In fact, within any given layer, there are no data dependencies whatsoever. So in terms of processing this, instead of processing this one neuron at a time, we can actually process a group of neurons, and we can exploit some data level parallelism here. So let me walk through a quick toy example of how we do this. So we start at the top of the network here, and we read a single activation value from the input vector, and that gets multiplied with unique weights, and the sum of that accumulated in the neurons. And we walk through the input data, accumulating all those values. And then when we've done that, we can add what's known as a bias term, and then we can apply an activation function. And then these values are finished, and we can store them back for use in the next layer. We can walk through the graph in the same way until we finish the output layer, and here we're done. So I think that toy example shows a really tiny, fully connected network processing 4 neurons at a time. But it raises the question of how much parallelism we can exploit. So as we increase parallelism, we get more throughput, but actually it also improves our efficiency. The reason for that is because we can get data reuse. So every time we read a value from the activation value from the previous layer, we can reuse that across all our parallel neurons. So this blue line here shows that as you increase the SIMD width, you can actually reduce the number of data reads. But increasing parallelism, it also increases the memory bandwidth, and I'm mainly talking about the weights here. And usually in computer architecture, the compute's sort of constrained to some degree by memory bandwidth, and the same's true here. So in this design, we sort of targeting quite low-end systems, so we stick to 128-bit per cycle bus interface. This still gives us sort of 10x activation reuse in a sort of practical system. So how do we implement this in hardware? Here's a simplified block diagram. I'll quickly walk you through how this works. So the host processor loads some input data into some buffers, and it also sets some configuration registers. And then most of the time is spent here. So here we're actually doing lots of multiply accumulates here in this SIMD data path. This is fed with activation data from these buffers here, and it's fed with weights from sort of a tightly coupled memory on the chip here. It's worth noting this memory is actually on chip, because if we have to go out to DRAM to fetch weights, then we'll immediately blow our power budget. So the MAC units here use sort of optimized 16-bit fixed point precision. They can also use 8-bit as well. The smaller, the better for sort of power. And there's a number of programmable features, mainly related to things like rounding and, I guess, the network topology as well. And then once we've finished all our neurons here, they accumulate here, we have an activation stage that adds bias, applies activation function, it writes the data back for use in the next layer. And these buffers are double buffered, so we can read values from the previous layer right back to the current layer. And then when the accelerator's finished, we can send an interrupt to the host processor, which can then go ahead and retrieve the output data. Okay, so yeah, an interesting point that's been raised already is that neural networks, we can often operate on sparse data with small data types. So again, I'll show, in this architecture, we kind of explicitly exploit sparsity, and I'll show how that works here using this toy example again. So often, input data to neural networks itself is also sparse. So we start with the input data, and we threshold the values to try and find numbers that are effectively so small that have negligible impact. And those are represented by the red nodes here, so we can basically not bother to store those back, so get rid of them. And we do that, we sort of prune the network in the following layer, and this reduces how much work we have to do. So this is good. And when we get to process the first hidden layer, you can see now we only actually visit 2 nodes. That's diagrammatical, but it's obviously much quicker. And then with these values, we can threshold these as well, and we get more of these red nodes, which we don't bother to write back. We can chuck them away, and that prunes the connectivity again. And we can kind of proceed to hash through the network in that way. And so that's obviously diagrammatical, but I hope that shows that you can sort of massively reduce the amount of work you do here. So in some previous work, people have sort of introduced pipeline bubbles to stall on small operands. But here we actually don't even store them back, so as we calculate them, we're actually pruning them out of the network. So to implement this in the neural network accelerator, we just make a few modifications. Okay, so broken animation here. So firstly, we introduce a comparator here, which basically compares the values as they're coming out of the data path and decides whether to keep them or not. That generates a signal that we can then use to predicate the write back here. And then we also need to store a list of the active nodes in the network, and we need this to generate the correct addresses for the weights, so we pull the weights out in the right order. And we also have support for 8-bit and 16-bit weights, which is pretty common, but gives you a nice efficiency boost as well. Okay, and then algorithmic resilience. So I won't go into this in great detail, but neural networks are basically trained to be error tolerant or tolerant to noise. And in fact, when we're training the networks, we actually often add large amounts of noise to prevent overfitting. So this is a really interesting property for sort of computer architecture. And we had a paper earlier in the year which was kind of included a bit of a deep dive on this particular aspect. But I'll quickly mention it here. So here we actually, in the accelerator, we can actually lower the supply voltage of the design to the point where the logic circuits actually start to fail. They don't always give the right answers. And we have some instrumentation on the chip that allows us to, for these 2 critical stages, allows us to monitor how often that happens. And the punchline with that is that for smaller networks, we can get really high error tolerance, so we can operate with really high error rates, and it has a negligible impact on the ability of the neural network to make accurate classifications. So this is particularly true for memory here. It's less true for data path logic because errors tend to accumulate for a long time in the accumulators. But in this paper, we kind of showed some tricks. We can sort of help out with the data path and get a really high timing violation rate on the combination. Okay, so I'll just run through some measurement results. So we implemented the accelerator in a microcontroller-based SoC. So it's ARM Cortex M0. And there's various sort of peripherals on here, some memory for various things. Here's the accelerator here. So we have a 1 megabyte SRAM to hold the model for that. And we have various supply voltages and clock frequencies, so we can play around with different performance points. So here's a package chip. This is a sort of flip chip package, 16 nanometer die. Here's a photo of development board, a snazzy purple laptop. And so this design's programmable, so we can run lots of different neural networks on this. And here's some measurement results. So these are energy per prediction. So this is how much energy do I have to draw to do a classification, single classification. And these are lots of different sort of always-on type applications. So these are well-known MNIST data. This is handwritten digit classification. This one is binary face matching. This one is spotting keywords in audio. And these are kind of interesting. These are human activity recognition workloads. So these try and detect poses like standing or sitting and so on. So the energy depends on the network for a number of reasons. These are all at the same throughput. But in practice, for real-time applications, some of these you'd want to run quite a lot faster. Maybe you want to run imaging applications at 60 frames a second, for instance, whereas maybe activity recognition you can do once a second or even less. But the energy shown here vary because the networks are of different sizes. So you have to do more or less work depending on what you're trying to do. An interesting point is that we often care a lot about accuracy from an application point of view, but it can be really expensive to get high accuracy in these networks. So often, in fact, it's exponential, or the energy is exponential with the accuracy. So example here, these two networks are basically for the same data set, they're the same problem, but the first one achieves a 0.3% accuracy increase, but that costs us 2.5 times more energy. And then finally, on this slide, as I mentioned earlier, it's really critical to have on-chip memory for these applications, and that's quite tough because they require a lot of storage. But of course, if we even fetch a few kilobytes from DRAM, we'll immediately blow our power budget. So this kind of constrains the model size. Okay, and then digging into some sort of lower level numbers here. These are measurements, so these kind of show with various techniques, how much power you can save. So if we start off running inference at sort of sign-off frequency 667 megahertz at the nominal supply voltage, if we then go to 8-bit data, we can reduce our power. This is basically because we're fetching much less data. And then we can also reduce supply voltage. Some voltage scaling to sort of win back margins in typical conditions. And finally, we can also turn on our optimization to exploit sparsity. And at that point, we sort of have an aggregate improvement of about 10x on energy. So it kind of shows if you do the hardware design, you can really eke out big performance gains. Okay, so this is kind of a survey to look at some published results in this sort of area. So there's been quite a lot of work in the last few years on sort of hardware design for neural networks. These are quite hard to compare, so take this with a pinch of salt. These are in different process technologies, and they sort of have different throughputs and so on, so it's probably not entirely fair. But the idea is to try and compare not just things like GOPS per watt and so on, but actually look at it for a given problem, what sort of energy can you achieve at what accuracy? So that's the motivation here. So some of these results are for spiking neural networks, which have been quite well motivated for sort of low energy problems. So this green one here is the IBM True North design, and this is a paper from Michigan University. And I mean, these are in older technology nodes, but it does seem like spiking neural networks seem to struggle to achieve good accuracy without resorting to large parallel classifiers, so what they call ensemble techniques. And these are really inefficient in energy. CNN architectures do really well. This is actually this is the MNIST data set. CNN architectures do really well for computer vision applications, and more recently they've also become popular for things like speech, which is really interesting. However, a lot of CNN accelerators are sort of target quite big computer vision classifications, which require DRAM storage. And this is our work here. The smaller stars here show a trade-off we can achieve just by changing the size of the network, so using less parameters. And I think the final point here, this is what is interesting, that this is the region that is kind of interesting from an accuracy point of view, because below here we can actually, the problem becomes pretty trivial and we can use much simpler techniques to solve it. So in the future, the next 10x on this, I think, is pretty likely to come from algorithm innovations. There's some interesting comments in previous talks about further compression techniques, which I think are going to become really important. Okay, and then some more recent work. As I said, neural networks have become quite a well-studied problem in the last few years. There's a large amount of money and research effort behind that. One of the challenging things with a lot of the work on accelerators is how do we actually realize speed-ups in real systems? These systems tend to be sort of predominantly software-driven. So this is something we've been thinking about recently at Harvard. Things like how do we actually interface the accelerator to the SoC? And then how do we map, if we have a larger system that might be heterogeneous, how do we map an arbitrary neural network onto that hardware efficiently? And then how do we provide abstractions that allow software to then use those accelerators and spawn off jobs? So a recent chip we worked on at Harvard in collaboration with ARM was this one. So the idea here really is to have an SoC platform that has all those ingredients. So it has custom accelerators, and it has interconnects, and it has CPUs, and so on. And sort of the idea is to have a platform for that. So that taped out recently. Okay, so just wrapping up, here are some high-level takeaways. You slept through the rest of the talk. Pay attention now. So some of the things I talked about are that there's a bit of a trend to try and move inference on mobile devices sort of back onto the device, so to avoid this loop via the cloud. Always-on sensing is a big driver for that. I described our accelerator architecture, which exploits parallelism, data reuse. It operates on sparse data with small data types, and we also mentioned algorithmic resilience. I presented some measurement results of our 16-nanometer test chip. Some of the takeaways from that are that it's really critical at these energy levels to store the model in on-chip SRAM, or at least on-chip memory of some kind. This particular work showed about 10x improvement in energy through various circuit techniques. So that's not compared to software, that's compared to a baseline architecture. And also we got about 4x throughput benefit as well, so that's from the sparsity optimization. And we show we can actually perform predictions at below 1 microjoule per inference. And then got a few minutes, so a few gratuitous plugs. If you're interested in deep learning, we recently did a synthesis lecture, a book on this topic, so I recommend that for more reading. And I work on research in Boston, so we have a machine learning group there, and we're hiring. We're trying to grow the group, so if you have any students or postdocs who are finishing up soon and want a job, come and speak to us, or point them to this web link here. Okay, I'm done.